So here is where we are in the bigger scheme of things. Remember, the strategy was to make use of the Hamiltonian formulation of dynamical theories in order to do the quantization, because that's where we have the canonical commutation relations in the Hilbert space. On the other hand, we also want to make use of the Lagrangian formulation, because that's where we can formulate things covariantly and get them ready for general relativity. Really, ultimately, that's a shame, because it shouldn't be that we have to go back and forth between the two formulations to pick up one benefit here, another benefit over there. But that's how we have to do it, because that's the best we can do nowadays. I'm hoping that one day one of you will figure out a way to do this elegantly. Now, usually, this back and forth is done in a flash. I don't think we should do it in a flash, because somewhere in this is a bug. And as I said, one day, one of you hopefully will figure it out, so that we can do the benefits of both frameworks in one go, right? So let's do this carefully. So we started with this step here. We defined the Legendre transform that gets us from the Klein-Gordon equation, and let's call it first quantized, because the fields phi don't have a hat yet. So it's just like the Schrödinger equation, where the wave function doesn't have a hat. Okay, so just the Klein-Gordon equation as a where the phi is a number-valued field, right? So we start with special relativity, first quantization, in the sense that the fields don't have hats yet, in the Hamiltonian formalism, and then we Legendre transform that, and we are still in special relativity at that point, still first quantization, but now we have it in the Lagrangian formalism. This is the formulation in which we can then generalize to general relativity. But then we are in general relativity and don't have a Hamiltonian. So we have to go back to the Hamiltonian formulation, and then we can quantize that. Okay, so here is what we did. We started with the Hamiltonian, which is a function of the field and the canonically conjugate field pi, and then we Legendre transformed that to the Lagrangian, which depends on phi and the Lagrange and the Legendre partner to pi, which we might call beta. Okay, so a priori this is a function of two variables, phi, the phi field and the pi field, and then the Legendre transform treats the first variable phi as a spectator variable and turns the variable pi into the variable beta. Okay, so as far as the Legendre transform is concerned, it doesn't know a thing about dynamics. It just treats this as a function of two variables, a function of that get maps into a function of two variables. And the relationship is this, that that beta can be expressed as dh by d pi, and pi can be expressed as dl by d beta. In this way, we go back and forth. I'm using the acronym T for the transformation between Hamiltonian and Lagrangian. Now, as I said, the Legendre transform in itself doesn't know anything about the dynamics. It just treats functions and maps them into other functions. The proposition now is that the Legendre transform, when applied to a function h, which is actually a Hamiltonian, with these equations of motion, namely that phi dot is dh by d pi and pi dot is dh by d phi, then after the Legendre transform, these equations of motion become those equations of motion. So let's call them h1 and h2 on the Hamiltonian side and L1 and L2 on the Lagrangian side. So these, remember, are the Hamiltonian equations, and these are the equations for the Lagrangian, the Euler-Lagrange equations. Two equations go into two equations. Here they are. At this point, it may not be so clear why this is a beneficial thing, because remember, the reason why we want to do the transformation in the first place is that the Hamiltonian formalism treats time specially. Whereas in order to get consistency with relativity, we need a formulation that treats space and time the same way. It doesn't look like these equations treat space and time the same way, so we will have to study exactly how the fully covariant framework actually arises. So let's see why it is that these two equations of motion are equivalent to those equations of motion via the Legendre transform. Let me just give an example of how you can prove these things. So the claim is that H1 and H2, that's the logical symbol for and, H1 and H2 are equivalent through the Legendre transform to L1 and L2. Let's show that the Hamiltonian equations imply the Euler-Lagrange equations. So let's see. L1 is this equation here. Phi dot is beta. How does it arise? All we can use is the Legendre transform definition and H1 and H2. From that, we want to derive these two. Okay? So we need to show that phi dot is beta. How do we do that? Well, we can use H1, H2, and T. We use H1 to say that it is dH by d pi, and then we use the Legendre transform to say that this is beta. So there we go. We have proved this equation. Let us show L2. Let us show that the Euler-Lagrange equation holds. All we have available is H1, H2, and T. So what do we have? Remember, this is what we have to show. Let's start with this. d by dt of dl by d beta. So d by dt, dl by d beta is, because of the inverse Legendre transform, we have that dl by d beta is pi. So we have that d by dt, dl by d beta is d by dt of pi. But then we can use the second Hamilton equation and write pi as dh by d phi. Then we express h in terms of L using the Legendre transform. So this is just another way of writing down what h is. And then we carry out the differentiation with respect to phi. And we get a phi dependence in here, and in there. 3 occurrences of phi. So we get dl by d phi. That's just the direct dependence of L on phi. That's this. Then we have a phi dependence in here. So we have a d beta by d phi. That's this term multiplied with a pi. And then we have this phi dependence, which is dl by d beta, and then d beta by d phi. Remember, this is just the usual Legendre transform. New variable times old variable minus the old function. Well, and then dl by d beta is, by the definition of the Legendre transform, just pi. So we have that this term matches that term up to a sign, goes away, and we have dl by d phi. And that is what we had to show, that this is equal to that. This was the second Euler-Lagrange equation. Okay, so all of that is quite straightforward. You may want to exercise your skills by doing it in the other direction. Now, the Legendre transform to the Lagrangian formulation allowed us to rewrite the Hamilton equations of motion in this way. But why is that good? Or why is it any better than the Hamiltonian formulation? After all, as I said, we want to get a formulation in which space and time are treated equally. It doesn't look like this is achieving it. It turns out that it takes a little bit of work to see how we get from here to a formulation that treats space and time equally. So let's analyze those two equations. Remember, L is a function of, let me put it up here, is the Legendre transform. L is a function of the field and of beta. They canonically conjugate to pi, where beta is related to pi in beta is related to phi dot as one of the Euler-Lagrange equations. Beta is not by nature phi dot. It is only phi dot because of the equations of motion. This is a small subtlety that will play a big role a little later. The main point is L depends on phi and on beta. So in particular, if you do a derivative, functional derivative with respect to phi, then you're really only differentiating with respect to this. If you're functionally differentiating with respect to beta, you're really only functionally differentiating with respect to beta. They are independent functions. Only the equations of motion later relate phi dot to beta. So this is the reason why there are space derivatives hidden in there that were not perhaps clear from the beginning. So when we differentiate dl by d phi in the equations of motion, in the second order Lagrange equation, then this is a total derivative with respect to all occurrences of phi. Remember the second order Lagrange equation? Here it is. dl by d phi is this. This is a functional derivative with respect to all occurrences of phi, not including phi dot, because phi dot is really beta, right? It's an independent variable. So it's a functional derivative of L with respect to all occurrences of phi. That includes clean occurrences of phi and decorated occurrences of phi, such as space derivatives of phi. So we will actually have here also derivatives with respect to spatial derivatives of phi. That's automatically included, because when we defined what the functional derivative is, the statement was just replace all occurrences of phi by phi plus epsilon times Dirac delta minus the original functional divided by epsilon, and then take the Newton-Leibniz limit. So all occurrences of phi, even space derivative, space differentiated ones, as I will show in a moment explicitly. But remember, the L naturally doesn't have a dependence on phi dot. It depends on beta instead. Okay, so dl by d phi is the total derivative with respect to all occurrences of phi in L, including, possibly, if there are, spatial derivatives of phi. Why? Now I'm saying the same thing with equations. What is the functional derivative of L with respect to phi? The limit epsilon going to 0, 1 over epsilon, just like Newton-Leibniz. Here's the functional with the argument phi replaced by, with the function phi replaced by the function phi plus epsilon times the Dirac delta minus the unadulterated Lagrangian, the unchanged functional. Well, and then 1 over epsilon, epsilon going to 0. And if this phi it comes up to the 7th power or differentiated and then exponentiated, doesn't matter. All occurrences of phi have to be replaced by this and at that position. Let us do an example. Let's say our functional that we want to differentiate is f of u. U is the function. F is the functional. And let's say this functional maps functions into a number in the following way. You feed it the function u of x, then differentiate it, then multiply it with the sign, and then integrate. Why not? It's just something you can do to map a function into a number. Then you might say, okay, if I functionally differentiate that with respect to u, I should get 0, because it doesn't depend on u, it only depends on the derivative of u. No, 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 that's not how it is. The functional derivative picks up on all occurrences of u. So it's not the case that the f by du would be 0 just because there is no undifferentiated occurrence of u. No, instead what we will get is that the functional derivative, what you get is that the functional derivative of f of u can be calculated in this way. Use integration by parts. If we use integration by parts, then the derivative ends up on this side. And then we have a u of x which is not differentiated. Now it looks like this. I'm assuming here that our u of x, as we will generally assume, vanishes at the boundary of the integral, or really at infinity, because we will integrate over all of r here. So no boundary term. Then we have that this functional can be equivalently written in this way, and now we see there cannot be any doubt that the functional derivative with respect to u should pick up something. And indeed what it will pick up, of course, is that it is minus of the cosine of x. So the functional derivative of f of u is not sine of x, it's minus cosine of x, as it happens. And that has to do with the fact that the u didn't occur just trivially, but it occurred with a derivative in it. Now, I used here the trick of integration by parts, but that would not have been necessary. In principle, it's a matter of, you just evaluate this by first principles. You just use this formula for it, and then at some point, you may want to do an integration by parts. But my point is that I didn't introduce any new rules. I just used this functional and that definition, and then that's what you get out. So similarly, the Euler-Lagrange equations L1 and L2 will also contain non-trivial time, and space derivatives.
Why wouldn't that work if it was a time derivative?
Well, our L, if it were explicitly dependent on phi dot, then yes, we could functionally differentiate it with respect to phi, and we would pick up a contribution this way. But our L just doesn't depend on phi dot. It depends on beta. But later we will cover that in exact detail. Yeah.
Integral over space, right? So you can't do this.
True. But if it were, yes, well, that's true. But in fact, that has to do with how the whole thing would resolve itself into a fully covariant framework. We will have to work with time integrals as well. But it's just regarding Natasha's question, yes, if you had a time integral, and if L had a dependence on phi dot, then yes, the same argument could be made.
Here, phi depends on t also, but when you put in the delta function, there's no t in there.
Correct.
Why is that?
That's correct, but it's because we have used in this framework t as a spectator variable, basically. It's when you define your functional derivatives, then, and you're dealing with functions of, let's say the functions have 20 variables, then you can always choose to hold some of them fixed and say, okay, the first and the seventh variable, I hold it fixed, so that I'm considering my function to be a function only of the 20 variables except for the first and the seventh. You can do that. And that makes a difference for the functional differentiation, because then you're not putting the Dirac delta for those two directions, for those two dimensions in there. And our definition of the functional derivative of our functions has been with respect to the space variables only. We treat the time variable special in this. And we will have to fix this today in order to get the fully covariant framework. Okay, so, but the message that I wanted to convey with this so far is that we know, of course, that the Lagrangian does contain spatial derivatives of phi, and therefore the second order Lagrange equation doesn't show it in this formulation, but this really will produce terms with spatial derivatives. It will depend on terms with spatial derivatives and will produce terms with spatial derivatives. But how exactly do they come up? Is there a systematic way to evaluate the derivatives with respect to the spatial derivatives? Basically, how can we systematize this business here? We have a functional, it depends on the derivatives, It depends on the spatial derivative of a function. And then we found, yeah, if you functional differentiate it, you get minus cosine. Maybe there's a general structure behind this. A structure that would say, yeah, just differentiate it as if it were an ordinary function without derivative. But don't forget you have to take the derivative of that because of the integration by parts, right? Now, clearly, we see that this is what's going on here. No matter what function you would have here, the end result would be the derivative over there, right? Now, what's the general statement if you have higher powers of the derivative of the function? Then what? And as you can imagine, what you will get is higher derivatives over there. So here's a lemma. Consider any functional z of the form that z feeds on a function f, puts out a number, and our functional is a polynomial in the derivatives of a function, of the argument. But then can show that the functional derivative of z with respect to f, according to the original definition of what a functional derivative does, really working out the Newton-Leibniz thing, and then on occasion perhaps using integration by parts, you find that it is minus d by dx of dz by the derivative of the function. So the general statement is that if you functionally differentiate a polynomial of a derivative of a function, then you can do this by taking minus the spatial derivative of the functional now differentiated with respect to the derivative of the function. Which means that this notation means use the usual Newton-Leibniz formula for functional differentiation, but don't functionally differentiate with respect to f, but with respect to d by dx of f. And clearly this is what would work in this case, right? What it says is that if you want to functionally differentiate this with respect to u, what you can do is you can functionally differentiate it with respect to the derivative, and then of the outcome, you still have to take the derivative. Right, so the key here is that the functional differentiation with respect to f gives us can be evaluated in one go, so that we don't have to do all those integration by parts, by functionally differentiating with this directly with respect to the derivative of the function, and then appending here minus d by dx to it. So for example, let's say our functional is this. It's take your function, take the first derivative, and square that, and integrate that then. And for simplicity, we will adopt the notation that d by dx of f can be written as del x of f. So what if we want to functionally differentiate that functional with respect to f? Well, according to the lemma, all we have to do is, we can do it by first principles, but we can also, and that's what the lemma says, we can functionally differentiate this thing in such a way that we interpret dx of f as the independent variable, and then just act with the derivative, or minus the derivative, afterwards on the result. Because that's what it says, right? Instead of doing it from first principles, you can also functionally differentiate with respect to the differentiated function, but then also apply minus the derivative after that. Okay, so if we do this, if we functionally differentiate this with respect to d by dx, consider this to be the independent variable, then of course we get that the functional derivative of this is twice dxf. And then our lemma says that you only have to attach to that, or do afterwards, a minus d by dx, So a minus d by dx of this, which is minus 2 d by dx squared then of f of x. So that would be the claim. And we can verify that from first principles. So we have d by df of z, limit of, and now it's really completely first principles. So all occurrences of f have to be replaced by f plus epsilon times the Dirac delta. So even within the derivative, right, the whole thing that gets differentiated here, the f is replaced by f plus epsilon Dirac delta. We take the derivative and square it, minus the unchanged functional. And when we carry that out, what do we get? We get the dxf squared, which we cancel with that term because that term has a minus. We will get a term that has 2 dx prime f times epsilon times the Dirac delta. And this is a term that will survive because it's proportional to epsilon, and there's an epsilon in the denominator. The epsilon go away. In the limit epsilon going to 0, that's the term that survives. And then there's a term which is epsilon squared, Dirac delta squared. But because it's epsilon squared and there's an epsilon in the denominator, there's one epsilon left over. It will go away as epsilon goes to 0. So the only term that we are left with is this one, the mixed term here from that product. It's twice this. Now we integrate by parts. Get this derivative over there with a minus sign, so with minus 2. Second derivative over here. And now the Dirac delta can be carried out. And we are just left with minus 2 second derivative of f, which is what we had by the lemma as well. And very similarly, we can do it for higher powers. And then the overall idea is that when you have functionals that are generic, we hope that they have a kind of functional Taylor expansion, and so it works always. Not really always. This whole business of Taylor expansions is very difficult to verify in quantum field theory, and without severe cutoffs, it's generally not true that you can Taylor expand them. I mean, you can Taylor expand them, but they may not be convergent. The radius of convergence of the Taylor expansion may be 0. Okay, so let us review now what we can now say. What can we now say about the Euler-Lagrange equation? The Euler-Lagrange equation was this one. The L by d phi is d by dt, the L by d beta. We can now use our lemma to say that, therefore, dl by d phi is equal to dl by d phi, where we differentiate here only with respect to the naked occurrences of the phi, and consider the d1 and d2 and d3 of phi all to be separate variables. And then we differentiate also with respect to the occurrences of those independent variables in L down here. So we then have also a dl by d del 1 of phi and so on, and dl by d2 of phi. And by the lemma, we also have, whenever we do this, we have to add an extra derivative with respect to the variable that in question here and a minus. Right? So by the lemma, we have that the full derivative of the Lagrangian with respect to phi from first principles is equivalently, you see, this is not the right-hand side. What I'm saying is that this thing is this, is that, right? I'm just saying that the full derivative of L with respect to all occurrences of phi is given by the functional derivative of L with respect to only the naked occurrences of phi and those extra terms to take into account the differentiated occurrences of phi, the spatially differentiated occurrences of phi, just by the lemma. So therefore, our second Euler-Lagrange equation now takes this form. You see, I'm just plugging, if we plug this expression here on the left-hand side, then we have that these two terms are equal to that term here on the right. Okay, so we have that dl by d phi, and that now means functionally differentiate only with respect to the direct occurrences, the naked occurrences of phi, minus functionally differentiate with respect to the differentiated occurrences of phi with the d by dx and the minus sign equal to the right-hand side of the Euler-Lagrange equation, functionally differentiating with respect to beta. And we also had, of course, that beta was phi dot. At this point, one would be tempted to conclude, therefore, that we can write the dl by d phi is equal to the sum from 0 to 3, not just from 1 to 3, but from 0 to 3, of d by dx. You see, after all, there's a d by dt here as well, and there's just d by dx's. And then we have the dl by d phi, where the L now depends on naked phi as well as spatially and temporally differentiated phi. This is almost correct, but we have to remember here that the true variable in here is really the beta and not the phi dot. You may wonder what kind of implication does that have? Well, let's see. You see, and this comes back to something that Ding raised earlier. If this were true, if we could just let this stand as it is, then that would suggest that we can now use our lemma backwards and simply say, okay, what this is saying is, by our lemma, that simply the full functional derivative of L with respect to all occurrences of phi, including the naked occurrence of phi, including the spatially differentiated occurrences of phi, and the temporally differentiated occurrences of phi, is equal to 0. Right? That is what that equation would seem to suggest. Right? So if we start with this, then by our lemma, we should be able to conclude that simply by spelling out that this is the differentiation with respect to all occurrences of phi, and if we drill down to the different kinds of occurrences, we would get that equation. Not true, though. Not true, because in order to apply the lemma to the derivative d by dt phi, we would need that L possesses a t integration, which, as Ding earlier pointed out, it doesn't have. Right? We have that, this is what the lemma said, but we had spatial integrations in this only, and not temporal ones. Our functional L is a functional that has only space integrals, but not time ones. This is why we have to introduce the action functional. The action functional depends on phi and its space and time derivatives, and it's the time integral over the Lagrangian phi and t. Okay, so S of phi is now the action of the field evolution. You plug in not just a field, but you plug in a field evolution. Phi, not just phi of x at a fixed t, but you plug in the phi of x for all t. And then you get a number out of that. Previously, our functionals were such that you plugged in a function, a field phi, and you got a number for each t. Now you get a number, just that's it. So you plug in phi of x and t, and you get one number out of that. Before, it still depended on t. So now, because we have an integration over t as well, we can apply the lemma in both directions now, both for spatial and temporal derivatives, and therefore it's correct for this integral to write down this equation. So what it says is that the functional differentiation with this, of the action with respect to phi, and that means the naked occurrences of phi, is equal to, or well, minus, the functional derivatives of phi with respect to the space and time derivatives of phi, supplemented with those derivatives, that is equal to 0. Or, using our lemma, we might as well say this. ds by d phi is equal to 0, where now what we mean is the first principle functional derivative with respect to phi, which means all occurrences of phi, differentiated or not. So that is what is meant by saying that the action is extremer in the classical case. It's the action principle. And the Euler-Lagrange equation is really nothing but spelling it out using the lemma, what it means for the naked phi and the derivatives of phi. If we spell it out explicitly, this thing, what it means is that ds by d phi is equal to 0, right? And explicitly it is that you have to take the action functional, replace all occurrences of phi, differentiated or not, all occurrences of phi with phi plus epsilon times the Dirac delta, the 4 Dirac delta, minus the unchanged action functional, divided by epsilon, limit epsilon going to 0. For example, for the Klein-Gordon action, the Klein-Gordon action is this one, time derivative squared minus space derivative squared summed over minus m squared d4x. And then try it yourself, either using the action principle directly, so first principles, functional derivatives, or use the lemma, use the Euler-Lagrange equations. Anyway, you will find that the Klein-Gordon equation comes out in this way, where the box operator stands for d naught squared minus the Laplace operator. The Laplace operator on flat space being simply the sum over the second derivatives. And this is, of course, on flat space, the sum of the second time derivative minus the sum of the second space derivatives. All of that will change with curvature. Now, yep.
So, in one example before you presented the lemma, you said that u should be 0 at the edges.
Yes.
It should be.
Yes, that's right.
So, maybe I don't have a good intuition, but phi should be a field defined in all space. So, what guarantees that? Like, what is the condition? Do we usually say that the field decays?
No, but the boundary terms can come up. If you have a situation where you care about boundaries, then it can come up. In general, though, we can assume that those fields vanish. Most of the time, we can assume that they vanish asymptotically. There is a difference between Schrödinger wave functions and those fields. A Schrödinger wave function, you're right, we don't assume to have vanished in the past and to vanish again in the future, even though we know that they should vanish at infinity, at spatial infinity to be square integrable. Now, our Klein-Gordon wave functions don't have that requirement. In practice, and this is a classical theory here, and what the action principle is saying is that among all the fields, those with the extremal action will be the ones that are realized in nature. And then, as you will see in a later lecture in this course, that generalizes to quantum theory by saying that all possible evolutions can occur, all possible phi of x and t can occur, and the probability amplitude for them occurring, roughly speaking, this is a fishy interpretation, but roughly speaking, the probability amplitude for this evolution to occur is proportional to e to the power of I times the action for that field evolution, phi of x and t. And this so-called path integral allows for all kinds of fields. And there is no restriction on the norm having to be conserved or anything of that kind.
So we can apply the lemma of the functional derivatives even though the field is not of compact support?
Well, you don't necessarily have to have compact support. It's just have to have non-contributing boundary terms. I'm not saying that the boundary terms cannot be important. They can be important. And ultimately, we know that in all of these discussions that we did today, there's a bug in there somewhere. I mean, it's not clear whether a subtler thing such as boundaries will save the day eventually. It's probably that a complete overhaul will be needed in order to have a unified picture in which both the quantum theory of the Hilbert spaces and the covariance of the Lagrangian formalism will coexist peacefully, and so that you don't have to meander between the two. It probably requires a complete overhaul, but who knows? Maybe this issue with the boundary is an angle to wedge in some good arguments. I mean, truth be told, nobody knows what the function space is that we have to path integrate over, what the fields are that can possibly occur. Okay, so we defined the action S of phi, and it had an integration over both space and time. And the function, the integrand over the four-dimensional integral is also called the Lagrange density or Lagrangian density. One often writes, and one often finds in textbooks, this equation here. Strictly speaking, that's not what we derived. What we found is that the correct Euler-Lagrange equations are obtained by functionally differentiating S with respect to the naked occurrences of phi and with respect to the differentiated occurrences of phi. Still, that equation, if you interpret this as being functional differentiations of the kind as we discussed, it's still correct. It's just that because the space and time integrals are missing in this, because L doesn't have the integrals in space and time, what you get from these functional differentiations is not what we got there, but you get what we got up there multiplied with Dirac deltas. Dirac deltas that would have gone away with the integrations. So basically, this gives you the Euler-Lagrange equations up to an overall factor of a Dirac delta, and assuming you keep in mind that these del's here really mean functional differentiation. But truly what's behind it is, of course, here, these two equations. That's really what's going on there. So if you want to revolutionize the field, maybe you know now what to look out for. You're up against. Okay, now we are basically ready now to go to general relativity. Because, as you can tell, this now is covariant. The Klein-Gordon action is completely covariant. That is conserved under Lorentz transformation. So let's introduce a bit of notation that will be very useful. Instead of writing the cumbersome space and time derivatives as d by dx mu, we adopt Einstein's notation of just putting here a comma mu, and in curved space-time that comma will become a semicolon. Also, we will adopt Einstein's notation to assume that indices that are occurring twice will be summed over. So for example, in an expression like this, because mu occurs twice, we know that it has to be summed over from 0 to 3. Also, you will define the metric tensor G mu nu of x and t. Now, I don't have time in this course to review all of general relativity, but the essential bits I will introduce, hoping, of course, that you know much more than that, but some of you may not be that familiar with it, so I give a very quick entry into this. So we define the metric tensor G mu nu of x and t. And so far, remember, we haven't introduced curvature at all. I'm just saying I'm going to introduce an object like this. And by definition, we will also call it eta mu nu for now. And by definition, it will be this matrix. With this definition, we can rewrite our Klein-Gordon action now. The Klein-Gordon action now takes this form. The space and time derivatives here. And the G mu nu is this matrix that will take care of the right kind of summation to occur here, namely there will be the square of the time derivative and then the negative of the square of the space derivatives, because G mu nu is going to be that matrix here. And then here's the mass term. A definition that I used here is G mu nu with upper indices. And the G mu nu with upper indices is by definition the inverse of the matrix with lower indices. But in this case, it's the same thing. This is its own inverse. So now the Euler-Lagrange equation. The Euler-Lagrange equation takes this form here. It's a little bit simpler because we replaced the cumbersome d by dx mu's by commas. So we have that the action depends on the naked occurrences of phi and the occurrences which have a comma as well. And then the Euler-Lagrange equation for the Klein-Gordon field in particular can be written in this form here, which is, of course, the same as writing it as box plus m squared phi equal to 0. So now we've definitely completed this step 1 here, namely that we went from the Klein-Gordon equation in the Hamiltonian formulation to the Klein-Gordon equation in the Lagrangian formalism and everything that goes along with it, the action and so on. Now we can start allowing curvature. And then from there, later on, we will go to the Feynman approach and the path integral, and everything will be covariant. But initially in the course, we will move on by doing the Legendre transform to the Hamiltonian formalism and then quantize from there. So how then will we introduce curvature? Well, we have a beautifully covariant Lagrangian formulation. The strategy for allowing curvature will be this. We start with special relativity. And in special relativity, we started by using inertial rectangular coordinate systems. That's how we worked all the time now. But from now on, let us allow other coordinate systems too. For example, spherical coordinate systems, or coordinate systems that people would use to go around on a carousel or in a plane. So we will allow arbitrarily deformed and accelerated and whatnot coordinate systems. And then we will see that from there, it's a small step to allow curvature. So here's how this goes. Remember, the Klein-Gordon action takes this form here. If we change to arbitrary coordinate systems, then what happens? If we change to arbitrary coordinate systems, let's say from x mu, which were our rectangular coordinate system, which was a rectangular coordinate system in Minkowski space, rectangular and set up by an inertial observer, then we know this is the right action. And then we change the coordinate system to coordinates x tilde, the x tilde being a function of the x. Well, then the field phi turns into the field, a new function, the function phi of x turns into a function phi tilde of x tilde, which takes the same output as phi, but you have to be careful with the input. So the output of phi tilde at x tilde is the output of phi at x corresponding to the x tilde. That's what a scalar function does. It doesn't change its output value, just the argument. But what that also means is that the derivative of phi with respect to space or time in the new coordinate system takes a different form. The derivative of phi tilde now with respect to x tilde is the derivative of phi with respect to x, according to this definition here, but followed by a chain rule factor dx by dx tilde. And what that means is that, in principle, if we change the coordinate system, the action would change because these things change by chain rule factors. But we want the action to be a scalar quantity that doesn't depend on any choice of coordinate system. I mean, this part is not changing with the coordinate system, that part is. So the idea is to transform this along with the change of coordinate system such that the action comes out the same so that it is scalar. What we can do is we can institute the rule that the g mu nu of x in a new coordinate system is defined to be the g tilde mu nu of x tilde with these factors here that are cleverly chosen to work together with these chain rule factors here such that in the action this turns out to be scalar, and therefore that turns out to be scalar. So this is the term in the action, and we know how these transform necessarily under change of coordinates. The g mu nu we now also let transform under change of coordinates according to this rule. And then this expression in the action, g mu nu d nu of phi, goes into, well, everything tilted here now. And then the tilted can be expressed in, the tilted g can be expressed in terms of the untilted g and these two factors here, those two. And these guys transform with chain rule factors, which are the same as these factors, but upside down. See, these have dx by dx, dx tildes by dx, and those have dx by dx tildes. And if you check, you find that they annihilate each other, and they just become Kronecker deltas. So that we have g mu nu of the derivative and the derivative the same way that we started out with it. The reason being that dx tilde by dx, dx by dx tilde, summed over equal indices, summed over these two equal indices gives us a Kronecker delta of rho and alpha. And that happens with these two, give us the Kronecker delta of alpha and rho, and these two gives us the Kronecker delta of beta and epsilon. Okay, so we say that g mu nu has been given the transformation rule as a contravariant tensor of rank 2. Contravariant means upper indices, and tensor of rank 2 means there are two of them. Remember that by definition, the g with the upper indices is the inverse matrix to the g with the lower indices, which means that we can also immediately tell what the transformation rule under change of coordinates is of the metric with the lower indices. It's the same thing as the one with the upper indices, except that those two factors are upside down, inverse matrices. And that now is called a covariant rank 2 tensor. Rank 2 again because it has two indices, the g with the lower indices, but it's called covariant because the indices are lower indices. Now, is the action coordinate system independent? No, not yet. See, the thing is that when we integrate something, then as we change in the four-dimensional integral the integration variable, we pick up a factor that changes the measure. Basically because as we go from one coordinate system to another coordinate system, we can easily have that the volume element gets stretched and squeezed. That needs to be picked up by this factor here so that we don't change the value of the integral. So as we change the coordinate system, this factor should occur. But then the action looks different. So that would mean that we have to cook up a new action for each coordinate system. We don't want that. We want to have the same expression for the action no matter what coordinate system we choose. Therefore, we have to put something into the action which will compensate the occurrences of these measure factors as we change coordinate systems. And remember, nothing about curvature just yet. This is just to make the action and therefore the equations of motion and everything else independent of the choice of coordinate system, to free ourselves, to liberate ourselves from the need of choosing rectangular coordinates, well knowing that in curved space there is no such thing as a rectangular coordinate system. On a curved space there is no chessboard with only right angles, generically. So we have to free ourselves from the need of rectangular coordinate systems, and that's what we do now. Okay, to finally succeed, we need that the action has something in it which absorbs the potential occurrence of such measure factors as the coordinate system changes, and yet we don't actually want to change the action. So we want to add a term to the action which, for flat rectangular coordinates, is just 1, just not changing anything, and yet it transforms the right way so as to absorb the measure changes as we change coordinate systems in a generic way. So what we do is we modify the action to include a so-called volume element, a volume factor, and the suitable thing to do for that purpose, it's a longer story to prove it, is to put the factor square root of minus the determinant of g mu. It's not strictly unique. You could put other things there too. There are other things that you could use as so-called volume forms. But physics dictates ultimately that this is what we should do. And it's also economical because it means we don't have to introduce yet something else. The g mu that we previously introduced is sufficient for the purpose. So if you take the g mu matrix with the indices lower, and take the determinant of that, the determinant actually comes out negative. And we know that because we know how it looks like in flat space coordinates. 3 minus signs, 1 plus sign. The product of the eigenvalues is the determinant, so that's minus 1. We multiply that with minus 1 to get something positive, take the square root of that. Looks a little odd, but why, why do we have to take that, why that expression, why the square root of it? Why does it, as I said, it's not unique, but let's see why it's not necessary to use that, but it's sufficient. Why would it be sufficient? Well, one can prove, this already said that, that this square root is 1 on flat space. So one of our conditions is being met. One of our conditions was that we want to change the action in such a way that we haven't really changed it as long as we work on with a Cartesian coordinate system. And we haven't changed it because that is just the number 1 if we work on flat space with Cartesian coordinate system. But one can prove, it's a longer calculation, that when we change coordinate system, then the square root of the absolute value of the determinant of g goes into the square root of the absolute value of the determinant of g times this determinant, which is just the inverse of the measure factor. The measure factor had a dx by dx tilde matrix, and this is the determinant of dx tilde by dx. And therefore, we now have, within special relativity, a formulation of the action S of phi, of a field phi, which comes out the exact same number independently of which choice of coordinate system you may want to use. Explicitly, it works out this way. Take the action, change coordinate system, then you get the action in terms of the tilde coordinates. And in terms of the tilde coordinates, the L tilde is L because we arranged it to be scalar. That's why the G had to transform the way it does. Then we get 2 determinant factors here. One because the measure changes, and the other because the determinant of the metric changes. And the two factors, by the way that determinants work, the product of two determinants is the determinant of the product. You can put it this way, and then this just becomes a Kronecker delta over here. And so the determinant of a matrix, which is just given by a Kronecker delta, is of course 1, and therefore we are back to the original action. So what we've achieved then is a formulation of the physics of the Klein-Gordon field, and that could be done very similarly for the electromagnetic field or for the Dirac field, a formulation of it which has a so-called metric tensor in it, and it's a formulation that is the exact same formulation no matter what coordinate system you choose. As long as it's a legal coordinate system, as long as it's a bijection from the original coordinate system to the other coordinate system, it's the exact same formulation for the action, and therefore for the Euler-Lagrange equations, and all of these things are taking the same form. All the complications of pseudo-forces and stuff like that come in intrinsically. They're just implied, but you don't have to spell them out. So it's beautifully covariant. And then how do we then allow curvature to occur? Well, that's very simple now. Consider what happens when you change coordinate system. So still flat space, just Minkowski space. And we change coordinate system. If we start with the Cartesian coordinate system, the metric takes this form. If we perform a Lorentz transformation, then, well, and that's how Lorentz transformation is defined, the metric keeps that form. If, however, we choose some wild coordinate system, then the metric tensor can take a very complicated form where all the entries take wild values as a function of space and time. It'll always be symmetric. G mu nu is G nu mu because of the way it transforms. Remember that the metric simply transforms in this way. In this way. So therefore, if you start out, as we always do, with a Minkowski metric, which is symmetric between nu and beta, then after an arbitrary change of coordinates, because these are the exact same matrices, the transform matrix will also be symmetric. But the matrices can be complicated. The change of coordinates could be very complicated. So what we get is all sorts of very complicated matrices G mu nu of x. If we look at all possible weird coordinate systems, we get, well, do we get all possible G mu nu of x's? We don't. If we start out with Minkowski space and perform all possible changes of coordinates, then we get a certain class, a certain set of symmetric functions, of symmetric matrix-valued functions. We don't get all of them. By just changing coordinate system wildly, we don't have access to all possible G mu nu of x that obey the minimum criterion of having the right symmetry and signature. So what we can do is, we can, now that we have a framework that has completely the same shape no matter what G mu nu of x we use, we might as well use that framework for G mu nu of x's which in no coordinate system become that. And it turns out that this is exactly the generalization that, that provides us with the opportunity to describe curved space and time. We still require, though, that the G mu nu of x are not completely arbitrary. We allow them not to have this form in any coordinate system, right? That is what gives us curvature. But we require that the G mu nu of x's that we will work with can always be transformed into that form at a point. if we didn't do that, then we could have signature changes. We would have suddenly 2 times or no time or 3 times, 4 times, right? So that we want to avoid. But apart from that requirement that there always ought to be a choice of coordinates such that at any point of our choosing, it becomes that matrix, then that's the right set of metrics that we will work with in general relativity. The statement that we still want that even though it can be anything wild, even though we don't require it to have a coordinate system in which it is this everywhere, the requirement that we still require that it has to have a coordinate system in which it is this locally at a point, maybe looks mathematically weird, but physically it's the equivalence principle. Right? Physically it says that it's always got to be a coordinate system. For every point that you may choose, always ought to be a coordinate system at whose origin you have this metric, and therefore in the neighborhood you have a metric that's very similar to this. This is the statement that locally in space-time, you can always find a coordinate system where you have the physics of Minkowski space. It's the freely falling elevator, or the freely falling coordinate system. Locally, if it's small enough not to feel tidal forces, then it will feel as if it were just ordinary Minkowski space. All right, so I think we are ready now to do the quantum field theory on curved space. We are a few minutes early today. Any questions?
So what about changing coordinates to a non-inertial frame? You know, you saw the inner effect. There's all sorts of effects. How does that pop into this formula? The action is not affected, right? Overall.
Yes, well that's right. But also keep in mind that so far that's classical, right? So just classical. Of course, yeah. If you okay, good question. Remember, we had this lecture where we studied the under effect, where we had accelerated observer, and we found that generically accelerated observers will, the accelerated detectors will click, and that indicates that the accelerated detector will see particles that nobody else might be able to see. Now here we don't talk about accelerated detectors, but instead it's coordinate systems that would be in which an accelerated observer could be addressed. See, it goes beyond an accelerated detector. An accelerated detector has merely a world line, which might be accelerated. But here we are talking about entire coordinate systems. So let's say you are an accelerated observer, you have a world line, and while you travel on that world line, you are setting up a coordinate system. And you're saying, I'm at the origin of that coordinate system. But that doesn't fix your coordinate system completely. You still have to say how you assign coordinates to all the other events, right? And so what you can do is you can say, I'm an accelerated observer, I put myself at the origin of my coordinate system, and I set up a complete coordinate system, not just the origin of it, where I am, but a complete coordinate system by some rules. And you're pretty free to choose the rules whichever way you want. And then you have a coordinate system, and then you look at physics in that coordinate system. Here we studied how you do the classical theory of that. You cook up your own coordinate system. This is how you get the action in that coordinate system. This is how you get the equations of motion, the Lagrange equations, all of that. But what about the quantum physics of you and your coordinate system now? Remember, now you're not just having a trajectory like our Andrew-Dewitt detector. No, now you have an entire coordinate system. And what you can do then is you can say, okay, I have this coordinate system. I'm now looking at a decomposition of the quantum field in modes that are natural for that coordinate system. That is going to be generally a mode decomposition that's non-trivial from the point of view of somebody who uses another coordinate system. For example, if it's in flat space, somebody who's using inertial Cartesian coordinates for an inertial observer. But also just in curved space between any two people who set up their particular choices of coordinate systems. They have two different mode decompositions of the same field. And now with each mode decomposition comes a natural choice of what you call your vacuum. And so if one of the observers then says, in my coordinate system, this state is a state of no particles, or that state is a state of so many particles, or that state is a state, a coherent state, and so on. Then another observer will agree on what the quantum field is, might agree on what the state in the quantum field is. I mean, they always agree. I mean, any two observers have to agree, what is phi hat of x and t? All observers will have to agree on what the state is that it is in, but what they might not agree on is which state is the zero particle state. Because they decompose the field into modes differently, and therefore they have different oscillators, and they have different states as their ground states. So they will not agree on what are the no energy states, what are the no particle states. They will not agree on what are the three particle states, and so on. And therefore, what for one observer is a universe with so many particles in it, for another observer will be a universe with that many particles in it, or even infinitely many particles in it. With this approach, you can also calculate the Unruh effect. And I'm planning to cover that then after the cosmology part of the course. So towards the end of this course, we will do the Unruh effect with this method, basically looking at the Unruh effect from the point of view of somebody who is not just an accelerated detector, but somebody who is setting up their own coordinate system, and then having their own mode decomposition there, and then calculating the Broglie-Wolf transformation between Minkowski space and the accelerated observer's frame. And then we will see that with this method too, you can calculate the Unruh effect, and you will find that if the acceleration is constant, then the modes will be seen as excited as if they were exposed to a thermal spectrum, the modes of the accelerated coordinate system. It's quite a non-trivial calculation, though, in the sense that it's not the same calculation as the one that we did with the accelerated Unruh Debye detector. Because when we calculated the accelerated Unruh Debye detector, we calculated the probability for the detector to click. We did not calculate for the field to do the one thing or the other. We calculated the probability for the detector to click. And that we interpreted as the probability for finding locally where the detector is, a particle. When we calculate the Broglie-Wolf transformation later, between what one observer calls, what in one coordinate system looks like the vacuum state, and what in another coordinate system looks like the vacuum state, then we are calculating the probability for certain mode oscillators to be excited. That's different. And the only link between the two calculations is really that both do indicate that constantly accelerated observers both see the same temperature. But it's a different physical question that's being answered with the two calculations. One is saying that an individual localized detector will be excited as if in a thermal bath. And the other calculation says that the mode oscillators will be excited as if in a thermal bath. These are not the same things. All right, and then once we'll do after we've done the Unruh effect in the with the Broglie-Wolf transformations, then from there it'll be a smaller step to, not that small, but still a manageable step to Hawking radiation. So I hope to do that then at the very end of the course. But first we'll do the cosmology. All right, further questions? No? All right, have a nice weekend then.